Hi everyone, I am P.NACHAMMAL, PG Department of Mathematics. Today we have to discuss some important topics in group theory. So in my PPT, we will discuss introduction about group theory and basic foundations in group theory like subgroup, order of an element, cyclic group, order of a group, cosets. So initially we start with the binary operations. So a binary operation on a set is a rule for combining two elements of the set. More precisely, if S is a non-empty set, a binary operation on S is a mapping from F in the Cartesian product of S to S. Thus F associates with each ordered pair x, y of an element S, also an element f of x, y of S. It is, we have to notation that x and y for f of x, y. Next, definition of a group. We have to say that a non-empty set G is a group under the binary operation. The following axioms are necessarily satisfied. First one, we have to take two elements A and B in a non-empty set G. So A into B belongs to G. Second operation with respect to associative, that is A into B into C equal to A into B into C for all A, B, C belongs to a non-empty set G. And third one, there is an identity element E belongs to C such that E left identity E into A equal to right identity A into E equal to A for all A belongs to G. Each element A belongs to G has an inverse element A inverse also belongs to G. Then similarly, left identity inverse element A inverse into A equal to A into A inverse equal to E. So we finally say that the non-empty set G is a group. Next, we say that the group is an abelian group or a commutative group. So if it must satisfies the condition A into B equal to B into A for all A belongs to A comma B belongs to G. Next, some examples of a group. Let G be the set of all complex numbers 1 minus 1 I minus I. So we prove that G is a group under multiplication. So similarly we check the first four condition. First one is closure, second one is associative, third one is inverse, and the final one is identity. So finally we say that G is a group under multiplication, and again we check that the commutative property of that group. So also the commutative property is satisfied. We have to say that G is an abelian group. Okay, for example, 1 power minus 1 equal to 1, minus 1 whole power minus 1 equal to minus 1, I power minus 1 equal to minus I, and minus I whole power minus 1 equal to I. Next example, the set of all rational numbers forms an abelian group under addition. Here the identity element is 0 and the inverse of each element is its negative. Similarly, we have to check the group under addition, that is set of all integers with respect to addition, the set of all polynomials and the set of all rational numbers are all abelian groups under addition. Next example, we have to check rational, real and complex numbers also abelian groups under multiplication. Next example, the translation of the plan R2 into the direction of the vector A comma B is a function which is a mapping from R2 to R2 defined by f of x comma y equal to x plus A comma y plus B. The composition of this translation with a translation G in the direction of C comma D is the function. F composition of G R2 where f of G of x comma y equal to f of x plus C comma y plus D, which is equal to x plus C plus A comma y plus D plus C. This is a translation in the direction of C plus A comma D plus B. This shows that the identity is the translation 1 with respect to R2, which is a mapping from R2 to R2, and the inverse of the translation in the direction A comma B is the translation in the opposite direction minus A comma B. Next, symmetric group. If S of x is the set of bijections from any set x into itself, then S of x under the composition is a group under composition. This group is called the symmetric group or permutation group of X. Next preposition, if A, B and C are the elements of a group G, then A inverse of the whole inverse equal to A, AB the whole inverse equal to B inverse into A inverse, and AB equal to AC or BA equal to CA, which implies that B equal to C. So we apply the both cancellation laws, left and right. Next, the definition of a subgroup. Some subset of a group will also form a group under the same operation. Such a group is called a subgroup. If G is a group and H is a non-empty subset of a group G, then we have to say that H is called a subgroup of G if the following conditions hold. First one, A into B belongs to H for all A, B belongs to H. That is the closure property. Second one, existence of inverse. A inverse belongs to H for all A belongs to H. Next, condition 1 and 2 are equivalent to the single condition, that is A into B inverse belongs to H for all A comma B belongs to H. Next preposition, if H is a non-empty finite subset of a group G and AB belongs to H for all A comma B belongs to H, then H is a subgroup of G. Next, the example, one set of all 1 minus 1 I minus I with respect to multiplication is the group, and the subset 1 comma minus 1 forms a subgroup under multiplication. Next example, the group Z, the set of all integers, is a subgroup of a group G, and P is a subgroup of X. Okay, the set n equal to set of all 0, 1, 2, 3, etc. of a non-negative integers is a subset of Z, but not a subgroup because the inverse of 1, namely minus 1, which is not belongs to n. This example shows that the preposition 1.4.2 fails. Okay, therefore the condition proves that H will be finite. The relation of being a subgroup is transitive. In fact, for any group G, the inclusion relation between the subgroup of G is a partial order relation. Next, the definition, order of an element. Let G be a group and A be an element of a group G. If A power k equal to 1 for some k greater than or equal to 1, then the least positive integer or smallest such component k greater than or equal to 1 is called the order of A. If no such power exists, means it has an infinite order. Next preposition, let G be a group and assume that A belongs to G has a finite order k. If A power n equal to 1, then k divides n. In fact, set of all n belongs to Z such that A power n equal to 1 is a set of all multiples of k. Next, cyclic group. If G is a group and an element A belongs to G, we write the generator A equal to set of all A power n such that n belongs to Z, which is equal to all powers of A. We have to say that the generator A is a subgroup of G, that is A is called the cyclic subgroup of G. The entire group is generated by A. A group G is called cyclic if there is some A belongs to G with G equal to generator A. In this case, we say that A is called a generator of G. Next preposition, if G equal to generator A is a cyclic group of order n, then A power k is a generator of G if and only if the GCD of k comma n is equal to 1. Next, important note, the number of generators of a cyclic group of order n is denoted by pi of n. Next preposition, let G be a finite group and A be an element of G, then the order of A is the number of elements in the generator A. Next definition, if G is a finite group, then the number of elements in G is called the order of a group and it is denoted by norm G. Questions, let G be a group with respect to multiplication and H be a subgroup of G. For element A comma B belongs to G, we say that A is concurrent to B modulo H, and we have to write it as A is concurrent to B modulo H if and only if A into B inverse belongs to H. Next, the preposition, the relation A is concurrent to B modulo H is an equivalence relation on G. The equivalence class containing A can be written in the form as HA, which is equal to HA, set of all HA such that H belongs to H. This is called a right coset of H in G. The element A is called the representative of the coset HA. Next example, we have to find out the right cosets of A3 in alternative group of order 3 in symmetric group 3. We have to take a coset in a subgroup A3 equal to set of all 1, the cycle 1, and the next cycle 1, 2, 3, and the third cycle 1, 3, 2. We have to take an element but not in the group, that is 1, 2. Then another coset is A3 of 1, 2, which is equal to set of all 1, 2, 1, 2, 3, 1, 2, 1, 3, 2, and 1, 2. So we have to take an element in the right coset form a partition of S3, and the two cosets above contain all the elements of S3. It follows that we have only two cosets, A3 equal to A3 of the cycle 1, 2, 3, which is also equal to A3 of 1, 3, 2, and again A3 of 1, 2 equal to A3 of 1, 3 equal to A3 of 2, 3. Next example, find the right cosets of H equal to identity element E and G4 and G8 in C12, which is equal to E, G squared, etc. G11. So H is one of the coset and another one is Hg equal to G power 5, G9. The two cosets have not exhausted all the elements of C12. So we pick an element, say that G squared, which is not in H or Hg. We have to take a third coset Hg squared, which is equal to G squared, G power 6, G power 10, and the fourth one is Hg cube equal to G3, G7, G11. Since the union of Hg, Hg squared, Hg cube, which is equal to 12, these are also the cosets of C12. Next, Lagrange theorem. Okay, there is a bijection between any two right cosets of H in G. So let HA be a right coset of H in G. We produce a bijection between HA and H. It follows that there is a bijection between two right cosets. Now we define a mapping psi from H to HA by psi of H equal to HA. Psi is clearly a surjective function. Now we have to take psi of H1 equal to psi of H2, that is the images are equal. Now we have to prove that the elements are equal. So we get H1A equal to H2A. Now multiplying A inverse on both sides, finally we got H1 equal to H2. This shows that psi is a bijection. Next, if G is a finite group and H is a subgroup of G, then order of H divides order of G. So this is a very important theorem in group theory. So proof, the right coset of H in G form a partition of G. So G can be written as a disjoint union. So G can be written as HEA1 union, HEA2 union, etc. Union HEAK for a finite set of elements A1, A2, A3, etc. AK in G. By using the lemma 6.2.1, the number of elements in each coset is order of H, and the number of elements in G, that is order of G equal to K into order of H. Therefore order of H divides order of G. Next, H is a subgroup of G. Now the number of distinct right coset of H in G is called the index of H in G and is written as order of G over H. The following is a direct consequence of the proof of Lagrange's theorem. If G is a finite group with subgroup H, then order of G over H equal to order of G divides order of H. Next corollary, if A is an element of a finite group G, then the order of A divides the order of G. Thank you.